Thanks everyone for being here. It's a pleasure for me to be back in Bristol. I was just telling them, I think the first time I was here has been 10 years ago. And I've been visiting about once every 2 years. So it's nice to see, old friends and also to meet new people that are here in the unit. Sorry, I'm not going to be talking about Mendelian randomization today, but I am going to be talking about causal inference, so hopefully you're interested in that. So the title of the presentation is very ambitious, and soon you're going to realize that this ambition has to be turned down by assumptions that we need to make. So this is the structure of my presentation, and I wanted to start our conversation, and please feel free to interrupt me at any time, about this problem, right? The problem of unmeasured confounding observational studies. This, as you all know, is one of the main limitations for drawing causal conclusions from observational or non-experimental data. Of course, there are other sources of bias as well, but we're going to focus on confounding. So, the good old thing, we have a treatment or exposure or risk factor, whatever you want to call. I'm going to call it X. We have an outcome, a disease, something like that. I'm going to call it Y. And then we have a set of covariates that I'm going to call collectively as A. And what do I mean by that? I mean like a set of covariates that we selected based on a dash, based on prior knowledge, whatever, that we think may be good enough to eliminate confounding when we adjust for it. Okay? And the thing is that there is often uncertainty in whether or not A is a valid adjustment set. We hope it is, but we're often unsure about it. Okay, do you understand? Okay. So the questions we could have if, say, we use the DAG to select A. So we could ask ourselves, were all relevant variables included in the DAG? Were all the arrows correct? The arrows of the DAG, were all of them correct? And even if all is correct, have we measured A appropriately so that when you adjust for the measured covariates, we're actually adjusting for the real covariates. So all of those things raise flags in our confidence about being able to eliminate confounding when we do observational studies. Okay. So it would be nice. Well, I perhaps should wait for you to say if it's nice or not, but I think it would be nice if you can have a tool that we can apply so we can empirically assess whether or not A is actually a valid adjustment set. I think we all agree that would be nice. So yeah, so that's the goal. The goal is to be able to somehow empirically assess whether or not A is a valid adjustment set. Okay? And I'm trying to be very careful with the words I'm using. So, assess the plausibility. I'm not saying prove that you don't have confounding or anything like that, because we're going to need some assumptions here. Okay. So to do that, we're going to use a theorem that we developed. I'm just going to read out the theorem first. So what the theorem says is that among all covariates that we have, we look at those that are associated with the treatment conditional on all other covariates. And if among those we find one that is also independent of the outcome, given the treatment and all other covariates, then A is a valid adjustment set. I know saying like that very fast is abstract, it's hard to understand, and even harder to believe in. So what I'm going to try to do during the rest of the presentation is try to explain to you exactly what this theorem is saying, then present the assumptions we need for A to be true, and then illustrate how it can be applied using an empirical example. So first, I want to all understand what the theorem is saying. I'm not trying to prove why it is true. I'm just trying to explain to you what it is saying. Okay? So for concreteness, suppose that we have 10 covariates. Okay? And they are indexed by A1, A2, A3, up to A10. Okay? We have 10 covariates. What are we going to do to apply the theorem? We're going to test the association between each covariate with the treatment, adjusting for all other covariates. So if I'm talking about covariate A2, for example, that means I'm going to test the association between A2 and X, adjusting for A1, A3, A4, A5, up to A10. So I'm going to do this for all covariates. And I'm going to select the ones that are associated with X, conditional on all other covariates. Suppose that we did that for all covariates, and those three, A1, A3, and A7, are the ones that were associated with X, conditional on the other covariates. So we're going to be looking at those three covariates for the next step. If no covariate is associated with X given all others, then we're done, and the method cannot be used. So looking only at the covariates that are conditionally associated with X, in our example A1, A3, and A7, we're going to test their conditional association with Y. So for example, we would test the association between A1, because it was one of the covariates selected in the first step, with Y, given X, and all other covariates. And you're going to do the same for A3 and for A7. And if one of those three associations is no, then we conclude A is a valid adjustment set. I'm not saying, I didn't give you any reason to believe in that so far. I'm just saying that this is what the theorem says. But now I think I should mention the assumptions we need. And we're going to do that by exploring more DAGs. Yay. So just as a reminder, again, A is always our candidate covariate set, and is made up in our example, to make things simple, of two variables, Z and C. And Z is what I called, quote unquote, our testing variable, in the sense that it is a variable that we know that is associated with X given the other covariates. So it's a covariate that satisfies the requirements of the theorem. So what we're gonna do now is we're gonna explore different scenarios, and we're gonna try to ask we're gonna ask the following question. In those particular scenarios that we're gonna look at, is Z conditionally dependent on Y given X and C? So the same old thing that I have been talking about, only if A is a valid adjustment set. If the answer is no, then that means that we need to impose some assumptions. And the assumptions that we need are going to be illustrated in the DAGs that we are considering. So let's start off. So now we have two DAGs. Notice that the bottom ones, they have unmeasured confounders, so they have a U. The bottom ones are exactly the same as the top ones, exactly that, with the exception that we don't have unmeasured confounder, we don't have a U. Other than that, the bottom and the top DAGs are exactly the same. Okay. So let us examine those DAGs with regards to the question that we have in mind. So let's consider first the situation in the bottom where we have no unmeasured confounders. So in this situation, let's look at DAG A. So in DAG A, if I were to test the association between Z and Y, given X and C, which is my test association, what will happen? Z and Y wouldn't be associated, except by chance or something like that. But I mean, there is no sort of mechanism that would induce an association between them. Okay, and this is because they are disseparated when I condition on X and C. And this happens in both DAGs. So I'm focusing on A, but this would happen in both DAGs. What will happen in the top DAG? Top DAGs, but let's consider the top A DAG. This is similar as what we have seen before. So if I adjust Z and Y for X and C, I'm going to have this path here, Z, X, U, and Y, that gets open because I'm conditioning on this collider. So on the top DAGs, I would have Z and Y deconnected. There is an open path between them, conditionally deconnected, and in the bottom DAG, I would have Z and Y conditionally disseparated. So when I have this separation, I have independence. When I have deconnection, I have association, if I assume that my DAG is faithful. So that's the first assumption I need to make. I need to assume faithfulness. So first assumption that we need faithfulness, so that if we have the connection, we have statistical association. Okay, let's consider the second thing. And I think this DAG and the next one I'm going to discuss are the most important ones to really understand what the method is doing. So, please feel free to ask questions about this. I mean, feel free to ask questions at any time, but particularly now. So, again, top DAG with unmeasured confounders, bottom DAG, no unmeasured confounders. Other than that, the two DAGs are the same. Question, are Z and Y deconnected given X and C in the top DAG? No, they are not, because X is no longer a collider between Z and U. What is the difference between this DAG and this DAG? The direction. So here I have no arrow connecting Z and X that is pointing towards X. That means that X is no longer a collider between Z and U. So for me to be able to detect unmeasured confounding exploiting collider bias, I need X to be a collider between my testing covariate and the unmeasured confounder. And one of the things that would prevent that from happening is that instead of the path between Z and X being directed into X, it is directed into Z. So I need to avoid this. And how do I avoid this? By making an assumption that I know that none of the elements in A, none of the elements in my candidate adjustment set are caused by X. And this would actually be the typical case because we often use pre-treatment covariates as, adjustment variables. But it doesn't have to be the case always, so we better make this assumption. Of course, it doesn't have to be pre-treatment if you know that a post-treatment variable is not influenced by X, but you need to make that assumption. If you only have pre-treatment variables, then you know this is going to be true. So second assumption, none of the elements of A are caused by X. Okay? This would often be the case now if all covariates are pre-treatment variables. So the next DAG, DAG D, again, situation with unmeasured confounders and without unmeasured confounders. And the implication of this DAG is very similar to the implication of the previous DAG. We have Z and X deconnected, but they are deconnected through a path that is not pointing towards X. And because it is not pointing towards X, X is no longer a collider between Z and U. But now the reason why this is happening is not because X causes Z, it is because both of them influence selection into the study. So if both of them influence selection into the study, then the path that's deconnecting them is not pointing towards X. That causes X to not be a collider between Z and U, and when I adjust for X, I don't detect that. So for the same reason as before, I need to prevent this from happening. And the way I prevent this from happening in my work, where I can make assumptions about how reality is by assuming that Z and S are disseparated, so there is no open path between Z and S, causal or otherwise, and X does not cause S. So this is important to understand. I'm not saying that X cannot be deconnected with S. I'm just saying that X cannot cause S. For example, if there is a common cause between X and S, then the arrow is pointing towards X, and that's really what I need. So if any of those two conditions, this separation of Z and S or X not causing S, if any of those two hold, then I'm good. And I'm going to prevent this from happening. But now we have this third assumption. So the selection into the analytical sample is either not caused by X or not associated with Z. And we need those two assumptions so that we know that Z and X can only be associated through paths that are directed into X. And we need that so that X is a collider between Z and any unmeasured confounder. So in the next DAG, This is a very simple one, just to make a quick point. The difference here is that we have y causing x instead of x causing y. And we could have that in our method. We could have that, but that would need, this will get a little technical, so I'm not going to discuss it, but the implication of allowing this would be to the need to make stronger assumptions about lack of selection. And because I can guarantee this by design, I'm going to stick with this. So I'm going to assume that I am in a situation that I know that I cannot cause X. So say a longitudinal study or something like that. Okay? And finally, the last assumption relates to measurement error in X, in the treatment, in the exposure, or in the respective. So we are going to represent in our DAG a mismeasured version of the treatment by X prime. So notice that we have no unmeasured confounder, so no U. Nevertheless, Z and Y are deconnected given C and X prime. And what I'm adjusting for X prime instead of X, because what I have in practice is X prime, right? So Z and Y would be deconnected even though we have no unmeasured confounder. So we will need to assume that X is measured without error. That's a big one. And again, this would get a little technical, so I'm not going to discuss it now. But this assumption is not needed if one settles with estimating the effect of X prime itself. And in some cases, it might be meaningful. But if you want to assume to estimate the effect of X, and you believe that what you have is an imperfect measure of it, then you're going to be in trouble. Well, unless X doesn't cause Y, but that's a detail that we don't need to discuss. That's the final assumption. X is measured without error. Again, if your goal is to estimate the effect of the measured version of the treatment, then you don't need that. But if your goal is to estimate the effect on some theoretical, perhaps a latent variable or something like that, then you need that. Okay, so I know that everything I said so far is a little vague. Not vague, but it's a little abstract. And perhaps it's difficult for us to see like how that could be used in practice. So what I'm going to try to do now is to illustrate how we could apply this method in practice. And not only that, but illustrate how we could go about thinking about the plausibility of the assumptions we need to use it. Because one big thing that I have is that sometimes we, apply the methods, we just make all the assumptions we need and we go with that. I think we should always carefully assess the assumptions we need to make. Not saying you guys do that. I mean, people do. I do that. We all do that at some point. So in our example, we have data from the 1982 Pelotas growth cohort in Brazil. So sorry, I should have said that I am from Pelotas. Pelotas is a small to medium-sized city in the very south of Brazil, so close to Uruguay. It's a long trip to Bristol. It's summer there now. All that good stuff. I was talking to Jib the other day, and he was telling me, "What are you doing here?" And I said, "I'm showing my commitment. I'm showing how bad I wanted to be here and all that." So yeah, we're going to be using data from this study. Our exposure is high for age at 2 years of age, and our outcome is IQ at 3 years of age. One thing that to keep in mind is going to come back to us later is that in Pelotas, and especially in 82, there was very, very strong social patterning, both in access in optimal conditions for physical development, as well as in conditions for optimal development of your cognition, your intelligence, and all that, which means that socioeconomic factors are likely to be the most important confounders of this association in this particular context. So we have data on about 2,500 individuals out of almost 6,000 at baseline. This should ring a bell with regards to one of the assumptions we need about selection. And I'm going to mention the covariates that we selected, but I just wanted to mention the result first. So without covariate adjustments, so just looking at the unadjusted association between height for age and IQ, we have that 1s the increase in the exposure was associated with 0.3 highest the units of the outcome. And when we adjust for covariates, the result goes down almost by half, or slightly more than half actually. So, but I mean, we still have, strong statistical evidence, that this association is not zero. But is there a residual confounding? So that's the exact same scenario I mentioned in the first slide. But now instead of calling things X and Y and A, I'm giving other labels to the same ideas. So that's what I want to know. I want to know if 0.15 is the true, is the true result, or if I should adjust for something, or if I should have not adjusted for something. Now that we have a concrete example, we're going to try to apply the theorem to it and see how it could help us. Remember, our theorem said that if we had one or more covariates that were associated, that were both one, associated with the treatment given all other covariates, and two, not associated with the outcome given treatment and all other covariates, then our covariate set is valid. So how can we check this? I mean, not check the assumptions, checking if the conditions of the theorem are satisfied or not. So we could sort of break this down in 3 steps. So in the first step, we identify covariates associated with X, conditional on the remaining covariates. And how can we do this in our particular example? We could simply regress length for age on all covariates simultaneously, so using, say, linear regression. And those that are associated with the treatment in this model are said to satisfy condition 1. So in the second step, we would identify covariates that are not associated with Y, conditional on X, and all remaining covariates. And we could do that in our example by regressing the outcome, which is IQ, on the treatment and all covariates all at the same time. And those that are not associated with IQ in this model are said to satisfy condition 2. And what do we do in step 3? We just check for overlap. So if you have one or more variables satisfying, one or more covariates satisfying 1 and 2, then we would say that our covariate set is a valid one. So in terms of implementation, is very simple. So here are the results in our example. So I'm just want to show you first the covariates we selected: socioeconomic position at birth, maternal schooling, an index of assets, maternal age, maternal height, a genetic score of height, sex, and birth weight. So these are the covariates we are checking to see if they are a valid adjustment set or not. So what was the condition 1 again? We wanted to identify covariates associated with the treatment, which is length for age, given all other covariates. And in our example, we had 1, 2, 3, 4, 5, 6, 7. We had 7 covariates that satisfied this condition. All of them except maternal age. So let us check condition 2. What was condition 2 again? We wanted to identify covariates that are not associated with the outcome, which is IQ, given the treatment, which is length for age, and all other covariates. And in our example, we have, out of the 7 covariates, this coefficient is for the treatment. So out of the 8 covariates, 4 of them satisfied condition 2. Of course, there can be a discussion about statistical thresholds and all that, but keeping it simple for now, we would have 4 covariates satisfying condition 2. And what was condition 3? Check for overlap. So we have those 3 covariates satisfying both conditions, satisfying condition 1 and satisfying condition 2. So our theorem would imply that our covariate set is valid. Question, are we done? Shall we just be happy with concluding that our covariate set is valid? So what about the assumptions? Are they plausible? What about statistical power? I'm making statements about lack of association. So I'm better make sure I'm well powered to detect even small associations. So let's think about all of the assumptions. That's why I listed all of them first, because we need to think about them. So in terms of the assumption that none of the elements of A are caused by X, all of the covariates are pretreatment variables, that one is very easy to sort of guarantee that it holds, then we're done. Y does not cause X. X was measured at age 2, Y refers to age 30, so very good. X is measured without error. That's not something that we can immediately guarantee based on design only, but you can, think about it. So in our study in Pelotas, this was not measured by like self-report or something like that. We actually measured the individuals in real time, so when they were actually 2 years of age. And we have a trained team, and people down there are very careful about, making sure that we know how to do anthropometry. So I would be very confident that we were successful in properly measuring length and gender. Of course, we knew, and because it's sort of age-specific z-scores, we also needed the birth date. And we knew that with certainty because the way we recruited participants to this study was that we were every day, we had a research team at all maternity hospitals in Pelotas. So if you were born on that day, you would be recruited on that day. So we knew for sure your birth date. So the information we need to calculate length of age is pretty well measured. And I'm not interpreting this as a proxy of a latent construct or something like that. I'm trying to estimate the effect of length for age itself. So yeah, I would be reasonably happy about this assumption. Of course, this could be complemented with sort of sensitivity analysis for measurement error or something like that, but something I didn't do for this particular presentation. So the next assumption we need to assess is faithfulness. Selection, which is the perhaps most interesting one, is going to be the last one we're going to look at. First thing, it is impossible to guarantee that faithfulness holds. That's something we should all know right at the start. But nevertheless, we can try to assess whether or not it looks plausible in our particular example. Remember when I said before that socioeconomic factors were the most likely ones to be the strongest confounders? And I mean, we have a reason for that, not out of convenience, because we actually believe that to be true. So let's think about this. Our covariate set so far seems okay. But if I remove my covariate set, all variables related to socioeconomic position, I am essentially introducing confounding. So I would expect my method to detect that. So when I remove important confounders, my method cannot detect it. Then it looks more like violation of faithfulness than, there's actually no confounding there. Because when I introduce confounding, I'm not detecting it.
I don't quite follow this. Could you go over it again?
Sure. The sort of rationale of the method is as follows. If I don't see an association between, any covariate with y given x and other covariates, then I would assume my covariate set is valid. I don't know that, if that's true or not. But in this case, I know that socioeconomic position is likely to be a very, very strong confounder. So when I remove it from my covariate set, I would expect that my remaining covariate set would be invalid. And because of that, I would expect that in this new scenario, my method should detect this bias. If it doesn't detect, I would be more skeptical of the fact that it didn't detect before. So that's what I'm trying to do. I'm trying to introduce bias to see if my method detects when I am introducing bias. So let me show the results and maybe that will be clear. So what I'm doing here, I'm doing the same thing as I did when I was checking condition 2, but removing from my model all sort of socioeconomic related variables. And why do I see? I see here that for maternal height, it was not associated with the outcome when I adjusted for socioeconomic position. Now it is. And this is what I want to see. For genetic score, it was not associated with the outcome in the full model. It is associated with the outcome in the restricted model. That's what I want to see. But look at birth weight. It is not associated with the outcome in the full model, and it is also not associated with the outcome in the restricted model. So I'm much less confident that birth weight was actually being able to capture confounding, because when I removed important confounders, it still didn't detect anything. So if I were to do all my conclusions based on birth weight alone, and I didn't do this sensitivity analysis, I would arrive at the wrong conclusion. So that's why, even though given all the assumptions that my theorem requires, this would be correct. But when I challenge the assumptions and try to check whether or not they're valid or not, I can identify some sort of mistake. So in the case of birth weight, I would be more inclined to think that this is a violation of faithfulness than, absence of confounding, because when I remove strong confounders, it doesn't detect. Whereas for maternal height and for the genetic score, when I remove important confounders, then they detect. And I did the same thing in the last column here, but I removed all covariates instead of only removing socioeconomic variables. So here, for example, is the association between maternal height and IQ, adjusting only for the treatment. Here's the association between the genetic score and IQ, adjusting only for the treatment, and the same for birth weight. And I see pretty much the same thing as I've seen before. So what are those results showing? They are showing that maternal height and genetic score are behaving as I would expect them to if faithfulness is true, whereas birth weight is not. Another thing that we did to try to assess whether or not the assumptions we were making are plausible, we used a negative control approach. So I think triangulation is one of the best approaches that we can use to try to, assess assumptions and all that. And the negative control that we used was school type. So when participants were about 14 to 15 years of age, we asked them if they were studying in a private or in a public school. And in Pelotas, this is very strongly socially patterned. The poorer population in general goes to public schools, and the welfare population generally goes to private schools. So that means that the negative control outcome is strongly socially patterned, like our treatment and like our outcome. But it is unlikely that length for age itself influences the negative control outcome. So this is a plausible negative control for the likely most relevant confounders, which are those related to socioeconomic position. And what did we see? So what we saw was that before adjustment for the covariate set, length for age in standard deviation units was 0.64 units higher among those who studied in private schools. But when we adjusted for the same set of covariates as before, the association vanishes, which corroborates the notion that the covariate set that we have is actually working. Otherwise, we would see a residual association between length for age and school type. How did we assess faithfulness? We assessed it in two ways. One of them was by comparing association patterns across different models. So comparing the full model with restricted models. And we saw that for two covariates, the results were in accordance to faithfulness. And we also did negative control results. So we still need to check the last assumption of selection. The first thing that we need to note is that the two covariates that presented expected patterns according to faithfulness, maternal age, and the genetic score, as well as the treatment, they all precede selection into the analytical sample, and this is because most of the losses to follow-up in our cohort have happened after 2 years of age. So we just have no guarantee that this assumption holds. It may well be the case that the exposure influences selection, because it might causally affect, probability of being followed up over time, and genetic score and maternal height might also be associated with selection in some way or another. But when we look at maternal height specifically, you only had 2% of missing it is a baseline variable. So it was measured for almost the entire cohort. And when we compared its average between those who were included in the analysis and those who were excluded from the analysis, we see pretty much no difference. This is in SD units, so it's very, 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 very small. So those who were included in the analysis have pretty much the same maternal height as those who were not included, which means that maternal height seems to be disseparated from selection, which would then indicate that selection is not affecting the association between maternal height with the treatment and therefore with the outcome. But it is possible that maternal height is correlated with eligibility. So not like loss to follow-up or some sort of missingness after study enrollment, but it could be related to factors affecting, entering the study at baseline, because it is a variable that was measured that relates to a period that is before the study starts. Let me explain what I mean. So in the 1982 birth cohort, the individuals started to be followed up when they were born. But maternal height is something that's prior to it. So it could be the case that maternal height is related to factors or itself influences whether or not you're gonna be eligible in the study. It could be related to in utero survival, for example. And if that were the case, then we could have problems. So even though there is very little evidence that maternal height is related to selection into analytical sample post-study enrollment, it could still be related to selection into the study, not into the analytical sample. I still need to do some more work with that to understand whether or not the selection into the study, sort of like being eligible, being part of the target population, is a problem or not. I actually think it isn't, but I'm not sure so far. But another thing that we have to keep in mind is that when we compared models 2 and 4, so the full model and the restricted models, we did see indication that maternal height as well as the genetic score were able to capture confounding, because they did not detect when I adjust for the most important ones, and they detect when I don't adjust for the most important ones. So they seem to be able to capture confounding. And the problem with selection is that they wouldn't be able to detect confounding. So the fact that they seem to be able to capture confounding is reassuring. And of course, this could be complemented with, typical strategies for dealing with missing data, imputation, weighting, some other stuff. I just didn't do it. What I tried to show you here is the importance of trying as much as you can to assess the assumptions that your method. And I was very surprised by the faithfulness thing, because this is something that almost everyone takes for granted. But in our example, we clearly see that it could well be violated. And the last thing we'll need to look at is power. We are making statements about lack of statistical dependence, and that's heavily dependent on how powered your study are to detect associations. So what we did in the paper, I'm not going to go through that now, is that we proposed some simple simulation-based power calculations you can do. And we did that assuming that the residual association between the exposure and the outcome was solely due to confounding. And when we did the power calculations for this particular example, we had 10% and 65% probability that both covariates, or at least one of them, will detect such residual confounding, so we're actually underpowered. So it could be the case that there is still unmeasured confounding, but we just weren't powered enough to detect. So you also wanted to look at this. You also want to look at your power. Otherwise, studies with small samples are going to be more likely to, have no indication of confounding just because of power. Good. So I think this is the last slide. And there are two more, but this is the last one in terms of content. So again, what was the theorem? If out of our covariate set, if we have at least one that satisfies those two conditions, one associated with the treatment given all other covariates, and two, independent on the outcome, given X and the remaining covariates, then A is a valid adjustment set. So it's a very simple idea in terms of the theorem itself, but I hope that I was able to express to you the importance of the assumptions. So this is only true if the assumptions are valid, and therefore the assumptions need to be carefully assessed, and if possible, triangulated with other approaches, such as a negative control approach. And of course, we do absolutely need here power calculations, absolutely, because we are making statements about lack of association. We don't need to assume that covariates are measured with no error, because our goal is to detect whether the set of covariates that we have is enough, regardless of it being properly measured or not. And the same applies for treatment and outcome, but there are some subtleties that I'm not going to discuss. We could do more on faithfulness in terms of assessing whether or not it is true. One approach would be cross-cohort comparisons, and the rationale would be that, it would be weird for faithfulness to be violated in the same way in different cohorts, because, it arises due to sort of cancellations of parameters, so that would be a little weird. And of course, you can do pre-registration of analysis protocol, so if you a priori say, oh, I'm going to test this, and these variables, there is less room for tweaking your covariate set until you see until you see lack of association, and you just report that. And another thing I wanted to stress is that even though we were focusing on, essentially a statistical approach to try to assess whether or not the set of covariates is true, that does not mean in any way that we should not use prior knowledge to select our covariates. And I mean, even from the perspective of this method, this is true, because the stronger our prior beliefs that A is a valid adjustment set, then the more confident we're going to be in the results of this method. Yeah, so that's what I wanted to tell you. I know it can be a little bit, abstract or hard to follow sometimes, but I think at least the implementation of it is pretty simple. And the point really is to say that this is a method that people perhaps could use, but being very careful about assumptions, right? And this is not particular to this method, just to be clear. This applies to any method, but I think I am the worst enemy of my own method, because I always stress how it can break. And if you have ever been to any of my presentations in the past, you know what's coming next. It's a picture of my family. So those pictures, I've shown them in my last visit 2 years ago. And those are the updated pictures. So here my wife is wearing the Santa Claus hat during Christmas. Here's the next Neymar, but with discipline and focus. This is my final message to you. Thanks for your attention. I'll be happy to take any questions.